that changed the world. In 1846, for the first time ever, a patient was put to sleep with ether, massive code that changed the world. In 1846, for the first time ever, a patient was put to sleep with ether, Massachusetts General Hospital in Boston. And after that, pain essentially was gone in surgical operations. But how did the world hear about this? It wasn't from medical doctors, it wasn't from journals, it was from a magician by the name of Robert Houdin, who heard about the story of ether as performed in Boston in the operation and decided to infuse it into his act. So here's what happened. He brought a, quote, volunteer on stage, it happened to be his son, and he opened the bottle of ether on stage and he had the son inhale some of it. And he immediately went to sleep. Put him down on the stage, and then he told the audience that ether had some magical effects. It could make people defy gravity. So he would suspend his son in thin air, ostensibly with the power of ether, and he would show that there was absolutely no way.
This scene will kill you the first chance it gets.
I need money. We're at the fight tonight.
There can't be two of us.
I am here to fight, like my people are watching.
Ethanol and sulfuric acid to make diethyl ether. Diethyl ether is a very useful solvent for many applications, and I will be using it to make Grignard reagents, which can only be done in anhydrous diethyl ether. What will happen during the reaction is an acid-catalyzed dehydration. Ethanol is able to take up an hydrogen from sulfuric acid, whereafter another ethanol molecule can attack that ethanol and kick off the water. It then forms an intermediate, a protonated diethyl ether, where the remaining hydrogen can be taken up by any molecule in the solution that can act as a base. So this can be either ethanol, water, or the sulfate ion. After this, the electron pair of the bond moves onto the ether, and the reaction is finished. So for the reaction, I only need ethanol and concentrated sulfuric acid, and for the purification, a saturated sodium chloride solution, a saturated sodium bicarbonate solution, and calcium chloride. So first, I set up a 3-neck flask in an ice bath and I add 90 ml of ethanol. I drop in a stir bar, add a thermometer, and wait for the ethanol to cool down. Then I attach an addition funnel that contains 80 ml of concentrated sulfuric acid and add it dropwise to the ethanol. When the addition is finished, I remove the ice bath and add a heating block. Now, I set it up for a fractional distillation, and this is what the setup looks like. I turn on the heating and add 250 ml of ethanol to the addition funnel. After a while, the solution reached around 130 C and started to boil, and white vapors were coming off the mixture. I put an ice bath under the receiving flask, and we can see liquid collecting relatively quickly, but there's also a lot of vapor. Now that I am collecting something in the receiving flask, I can open the addition funnel and drip in ethanol as fast as the drip rate in the receiving flask. During the reaction, I noticed that the fractionation column was too hot, and ethanol vapors were also coming over. The thermometer above the fractionation column read the boiling point of ethanol. Since the mixture in the flask has to stay about 140 to 145 C, I can't simply lower the temperature. Instead, I will try to cool down the column. The first thing I did was removing the glass mantle around it. This should allow the air to cool things down. But unfortunately, it wasn't very effective and the temperature stayed the same. Instead, I opted to wrap part of the column in paper towels and soak them in water. This turned out to be effective, and the thermometer started showing around the boiling point of diethyl ether. After doing this, I let it continue for a while and stopped the distillation when pretty much nothing more came over. So I removed the heat source and stopped the distillation. So here we have the crude yield of diethyl ether, which I will have to wash using the saturated sodium bicarbonate solution and the saturated sodium chloride solution. So I transferred everything to a separatory funnel and I poured in about 30 milliliters of the saturated sodium bicarbonate solution. The mixture started to bubble a lot, which means there's likely some sulfuric acid that came over during the distillation. Since the temperature of the distillate was too high during the beginning of the distillation, it is not too surprising that a bit of sulfuric acid came over as well. I let it bubble for a while, and then I mix it around with regular venting. I repeat this process 2 more times with the sodium bicarbonate solution and 1 time with the sodium chloride solution. Afterward, I remove the water layer and drain the diethyl ether into a beaker. I set the beaker in an ice bath and then added a bunch of calcium chloride to dry it. I cover it with a watch glass, swirl it around a bit to cool it down and let it sit overnight. When I come back the next day, it looks pretty much the same and I take it out of the bath. I transfer all of the contents to a flask, including the calcium chloride. Since the boiling point of diethyl ether is so low, I can keep the calcium chloride in the flask while distilling without having to worry about the water coming over. So I set it up for a regular distillation, and I don't have to add in a stir bar since the calcium chloride beads work nicely as boiling chips. It quickly started to boil, and the diethyl ether started coming over in the receiving flask. After a while the flask is almost dry, and not much more is coming over, so I stopped the distillation. So this is the final yield of diethyl ether. The yield came out to be 45%, which is lower than the protocol I was following, which had a yield of 70%. Since the distillate temperature was too high for part of my reaction, some ethanol instantly boiled over and wasn't allowed to react to form diethyl ether, which is probably why my yield is a bit lower. Anyhow, I transferred the liquid to an aluminum bottle that contains molecular sieves. I then add a very small scoop of hydroquinone, which acts as an inhibitor to prevent peroxide formation during storage. The recommended inhibitor concentrations when using hydroquinone is only 0.002%, which is about 3 milligrams. Since I don't have the analytical balance, I just put in a very small scoop, which is likely only a few milligrams. Now that it is finished, I can safely store and use my diethyl ether, which I will store in the fridge and use in one of my future videos.
All integers contain the digit 3. So the integers are the whole numbers. So I'm saying that almost all whole numbers contain the digit 3. It sounds strange, doesn't it? Yeah, because I can think of infinitely many numbers that contain a 3. Okay, I've got 3, 33, 333, 3,333, and so on, right? I can think of infinitely many numbers that don't contain a 3. 7, 77, 777, 7,777, and so on. So how can almost all integers contain the digit 3? So 23 contains the digit 3, 310 contains the digit 3, 9,002,023. So what about the numbers less than 10? Numbers less than 10. How many numbers less than 10 contain the digit 3? It's just 3, isn't it? Yeah, it's just one of them. Right. So one of those, just the number 3 itself. So what's the proportion of numbers? Well, it's 1 out of 10. So it's 1/10, it's 0.1, it's 10%. What's the next size up? Let's look at numbers less than 100. We've got 3, we've got 13, 23, 43, 53, 63, 73, 83, 93. You may have noticed I skipped off the 30s there, so we've got 30, 31, 32, 33, 34, 35. So I reckon we've got 19. 19 out of 100, that's 0.19. 19% is what I'm saying. So the percentage has gone up. Let's try numbers less than 1,000. Well, we've got the 19 we said already, right? But we've got all those numbers again, but with a 1 in front. Like it's 103 and 113. And then we get 200 and something. We get 400 and something, 500, 600, 700, 800, 900. And then we can include all the 300s, which I skipped there. So it's the 300, 301, 302, 300. Right, so it's 271. What's the percentage? It's about 0.271. 27%. It's going up. Now, did you notice the trick that we used for that last one. I said, think of all the numbers with a 1 in the front. It was the same copy, but with a 1 in the front, with a 2 in the front, and then there was all the 300. You can do this in general. Right. Let's say the numbers containing a digit 3, let's call that T for 3. Let's call these 10 to the power n. Right. Less than 10 to the power n. So these are the numbers containing a digit 3 less than 10 to the power n. If you want to find the next one, that's going to be 10,000. You take your previous number, times it by 9, and add on 10 to the power n. And you can find the next number. You can do that. So that will be the next one we're looking for. So there's a little formula there. So let's do it. All right then, I'm going to use my calculator. So 9 times 271 plus 1,000, and I get that number. 3,439. What's the proportion? It's about 0.3439. It's going up all the time, about 34% now. It's going up all the time. In fact, there's a nice way to work out how many numbers they're going to be with a 3. Imagine if I was allowed to write my numbers like this, right, with zeros. So that would be a 0, but with all these zeros there. This is a 4-digit number. So here's another one. Right. And here's another one. How many 4-digit numbers are there? It's actually 10 to the power 4. 10 choices there, 10 choices there, 10 choices, 10 choices. How many of them don't have a 3? Well, if I'm not allowed to use 3, then I only have 9 choices for that place. 9 choices for that place, 9 choices for that place, 9 choices for that place. So that would be 9 to the power 4. If you want to find out how many integers that contain the digit 3, it is 10 to the power n minus 9 to the power n. So these are all my n-digit numbers minus the ones that don't contain a 3. The proportion then is going to be this thing divided by this thing, just 10 to the n. So it's this. Bum, 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 bum. And what is that proportion? 10 to the n divided by 10 to the n is 1, minus 9 to the n divided by 10 to the n. Here's another way to write that, 9/10 to the n. That's the proportion that contain a digit 3. And what happens? Well, this gets really, really big. This fraction gets smaller and smaller and smaller, and it will go to 1. That will disappear. It will barely be worth mentioning, and that is 1. So it goes to 1. We say as n gets big. So this is getting closer and closer to 1 minus 0. As that gets closer to 0, as it gets big, this gets closer and closer to 1 minus 0. So the whole thing is going towards 100%. 100% of numbers contain the digit 3. And this is the proper technical definition of when I said almost all numbers contain the digit 3. Almost all sounds like a wishy-washy, vague expression, but in mathematics it has a proper meaning. And it means that the proportion is going towards 100% as you get more and more numbers.